Okay, looks like we are about to start. Okay, so first things first, thank you a lot. That's 9 a.m. It's been tough, so great appreciation to all of you that made it for today's session. And remember that you can ask questions on Slido. My name is Grzegorz Piwowarek, and today I came to you to speak about CompletableFuture. But this time, it won't be about basics. It won't be about super advanced stuff. It will be about those interesting and unintuitive things that most people skip over and pretty much get to know those details on production. Because it turns out that some method, they made some assumptions about how some method works, but in reality it does work in a totally different way. I'm an independent consultant working at Hazelcast, helping as a lead architect. Yes, you can make fun that I write code in PowerPoint. I also do workshops and blog a bit on my side. Well, it's been a bit recently, but I'm getting back to that. So, the main topic for today, asynchronicity. But synchronicity, it's something that's beautiful and simple. Imagine you have two methods, two lines of code, method A, method B, and method A starts, method A ends, and then immediately method B starts and method B ends, and so on and so on. That's simple, that's trivial, intuitive, and terribly slow. Because if you start thinking about our computers suddenly working simply in such way, working on one thing at a time, literally, that would be, let's say, not squeezing most of the potential. That's why we have asynchronicity, which means those two operations can flow in two independent ways. Method A, method B can start in arbitrary points of time. They can complete as well. However, this poses some challenges, because suddenly when you have no synchronization between two separate independent flows, well, how do you receive a value from that? Because, well, when I want to run stuff in parallel and I want to run stuff asynchronously, sometimes it's okay because I just want to have something being done as a side effect, but in most cases I'd like to get my value back. But how do I do that? So it turns out that we have this concept of future promise. There's been a few others in other languages as well, which is like a wrapper in a value with the temporal aspect to it, which means that you receive this container in which at some point in the future, well, hence the name, a value will appear as the result of the asynchronous computation. And, well, as you can see, the idea is pretty simple. However, in Java, we've been struggling with it a bit. So the good part is that any method call that you have in Java can become async. And that's something that we can do by ourselves. And as you can see, that's actually pretty simple, because once you have an executive service, in this case with one thread, you can just submit pretty much anything you want over in there. And this will be performed asynchronously. And as you can see on the left, you get this pretty convenient handle, which represents the result of that operation. However, in JDK, we had two basic implementations. Well, one of them is interface, but we have like two defaults we will fall back onto. One is the default implementation backing the standard future interface, which has been there since JDK 1.5. And then CompletableFuture since 1.8, which is kind of supposed to replace that. However, as you can imagine, it's not fully possible due to backward compatibility guarantees. And that original feature had some limitations. So imagine that we want to have a simple computation that returns some value, in this case 32, which means it will return an integer. And let's have a look at the API. So we have the get method. As you can imagine, that's a method that just blocks and waits for a value to appear. There's a cancel method, which interrupts the underlying thread if you wanted to. there's a get with timeout. There is some new fancy method from JDK, some newer versions. Plus there is cancelled and is done. So as you can see, that API is not super rich. So it's convenient if you just want to block and wait for a result. However, when you start thinking about more complex scenarios, like, for example, I'm starting multiple operations in parallel, but I actually care only about the value that returned first. Let's say I'm implementing my own, stock exchange broker, and I want to be able, and just to be sure, I'm issuing, let's say, a couple of parallel requests to currency exchange providers, and we only care about the one that returns first. So suddenly, the API doesn't really support anything like that. So you need to start thinking, okay, perhaps instead of returning value in the future, perhaps I could have a blocking queue. And inside that method that I'm running, instead of just returning pure value, I should be putting it in a queue. Then perhaps I should block in that queue and handle exceptions in a certain way. And suddenly it becomes, well, it's not rocket science, but it still requires you to do extra effort. Additionally, imagine you want to do work, something like, I schedule an operation, I get the handle to it, and let's say I just want to log it. So suddenly, it's not trivial to do that. Well, you would need to squeeze that extra logic into the operation that you are scheduling, on a thread pool. But if you get only the future, and you don't have control over over the producer part, suddenly it's becoming non-trivial. Also, if you start thinking about exceptions, as you can see, there's not much you can do here. I mean, you can handle a bunch of exceptions here. But if you start thinking about some form of fallbacks and recovery, that again becomes pretty tedious and difficult. And this is pretty much why Guava's listenable future became so popular. So before JDK 8, there was the common solution to the problem was to rely on listenable future from Google Guava. And it is a bit better because you can register callbacks on the future. So okay, already it's a huge step ahead. And if you can remember, before JDK 8, we didn't have lambda expressions. Or we actually did have lambdas before JDK 8. They just used to look like that. Probably one of the ugliest lambda expressions out there. But you still had a option to provide an anonymous code to a listener as a function. So, as you can imagine, it was pretty tedious and pretty verbose, but it was significant improvement on top of standard implementation of the future. And this is where JDK 8 comes into play and introduces CompletableFuture, which is supposed to be like natural replacement for listenable future as well. And there's a huge difference in how it behaves. So the biggest difference is that not suddenly this future is not bound one-to-one to the underlying thread, because that was the case in the past. If you start digging, you'll find something like a runnable future, which you can see is an interface that combines runnable and a future. So internally, there was pretty much one class that was both, would represent not just the return value, but also the operation itself. CompletableFuture is different. This is effectively just a big bag where you can get a value. It doesn't know anything about what threads are about to complete it. And what's more, it can be completed manually, which means F1 complete, let's say 42, and that works. So as you can see, we didn't really introduce any extra threads in here. Well, we did, but this is unnecessary. And it still works. So the main difference is that future suddenly can be completed by 0 threads or any random number of threads, which is pretty convenient if you start thinking about scenarios like, running stuff in parallel and let's say returning only the the value of the operation that completed first. And what's more, it became, if you go look over the whole API, it is pretty rich now. Because in the standard JDK, we had just a couple of methods. Now we are overflown with the number of methods. So, and that's pretty cool, because now you can go here and utilize that functional style, declarative style, and say, then apply something to that integer. Well, let's make that integer. You can do a bit more. You can say then run, and so on, which is all nice in declarative style, and they all return completable futures. So all those difficult operations that were required an extra effort in standard JDK, standard implementation of the future interface, were replaced with a pretty convenient and declarative style of programming. And that was a huge thing, because if you look closely, this is actually like the first ideas, first traces of reactive programming getting into Java. Because at the end, what they are doing here, this is like very basic ideas taken from reactive programming. However, this talk is not about the basics. If you want to learn the basics, there's a better place for that. Let's go into those interesting stuff that you should definitely know when you are discovering CompletableFuture. What's more, if you've been never exposed to CompletableFuture before, you still should be able to benefit from that session, so please don't leave. So one of the first things that's pretty confusing and it's really surprising for many people is the act of cancellation of a CompletableFuture. Because people have been playing around with standard future for a while, not shutdown, but submit, got used to the fact that you can go cancel, true, and, well, the operation that was supposed to, that operation here, well, it's not very costly, to be honest, would be, the thread would be interrupted and the operation would be stopped. However, that was possible mostly because we had that convenient one-to-one mapping. So I know that there's just one thread executing that operation here, and I have direct access to it. Since there's one-to-one mapping, I can just interrupt the underlying thread and the operation should stop. That's simple and intuitive. However, this becomes really tricky if you start thinking about CompletableFuture and one of its main advantages, which is now generating trouble. So we go over, let's go CompletableFuture, supply async, let's go for 42 as well. CF1 and cancel. Well, as you can see, the CompletableFuture also implements the future interface, so it has all the same methods as the original one, and like 60 extra. So what could go wrong here? Let's go to the docs. And that's the part that's quite often overlooked. Main interruptive running, that flag has absolutely zero value. It doesn't do anything with CompletableFuture. And it makes sense, because if you start thinking now about situations in which one future could be potentially completed by a number of threads, what do you do? If you want to cancel future and the operation that's supposed to complete it, so what are we supposed to interrupt? Are we supposed to interrupt one thread or all the potential threads that could potentially complete it? Well, that would mean interrupting all of the threads, right? Plus, it becomes a bit more complex if you start thinking about scenarios like this one. Imagine you've constructed that pipeline. So CompletableFuture returns one value. Then you go, then apply, then combine, then run. And if we cancel the last operation here, what should we actually cancel? Should we cancel only that part? Or shall we propagate the cancellation up to the root, to the original operation? Don't look at me, I don't know the answer. That's a complex problem, right? And that's pretty much why there's no way there's no way to interrupt the underlying thread. So here I don't have really good answer to you how to handle that. I'm just telling you it's not possible from the CompletableFuture level. If you are controlling the producer and the consumer side, you can pretty much know which threads are executing the operations, but CompletableFuture won't let you do that because it's just a bag with values. It's not tied to the underlying operation in any way. Well, sometimes it is, but not in a way that could help us here. By the way, if you fully control both ways, producer and the consumer, technically you can hack it up. So, for example, in one of my libraries, I'm using something like that. So I'm created my own future that extends the original future, which holds a reference to the task that's supposed to complete it. But that works only in a very limited scenarios where you are in the full control over producer and a consumer. So that's doable, but I wouldn't advise you to do that. So we've covered one of the basic API methods, but there are also a few others that are pretty interesting. And as I told you, the original future had issues, I mean, not issues, let's say had missing a couple of API methods that would help you, for example, wait for all the futures to complete, or let's say wait for the first one to complete and return the value. And we got those methods in CompletableFuture that allow us to do that. And those methods are all-of and any-of. And they seem to generate quite a lot of confusion. So let's see how that could work. So let's create, and as you can imagine, all-of, CompletableFuture all-of is used for waiting for all the futures to complete. So let's create one future. Let's create a second one. And we can go all of CF1, CF2. And that allows us to wait for, well, as the name suggests, all the futures to complete. So let's have a look at the result. And that can be already the first part that's quite surprising. So we are waiting for all the futures to complete. They are both integer type. And what we are getting here is a completable future with void inside. Which can make sense, because in this case, all-of is used more like a tool that's supposed to signal the fact that all the futures completed. That's the original idea. But still, I think it would be a bit more convenient to have a list of values that that resulted in all those operations completing. So let's have a deeper look here at the method signature. And this is, the longer you look at that, the more it might look confusing a bit. Because look, all-of, it accepts var args of CompletableFutures. I'm okay with that. But it accepts CompletableFuture with wildcard in here. Which means that I can have completable futures with different types, and the method will still accept them. And this is not a common scenario, because in most cases, when you want to wait for a couple of operations to wait, usually you wait for operations that return values of the same type. But I don't remember really scenarios in which I had to wait for a future with an integer, a future with a car, future with a string, and something else. But okay, that's a generic solution that lets you wait. So let's have a look. Let's have a look if that actually works. So we have that result over here. We can call .join. But before we call .join, let's call then accept, which allows us to print out the content of the future. So since these are two raw futures that are not completed by anything, well, we have a deadlock, effectively. So let's actually make sure that those complete somehow. In order to do that, I will create myself a helper method. I'll add a bit of delay here. So No, not here. I know that's not how you handle interruptions, but please forgive me. So to make it more interesting, let's param. So we introduced a very boring operation that just waits a second before returning a value. So instead of providing empty CompletableFutures here, let's go for CompletableFuture, supply async, process 1, and the second one will be 2. So let's run that. So we waited for the futures, we waited around a second, and we got a null inside, and that's accepted. That was expected, right? Because, well, there is void inside. So it makes sense. So if it turns out that one of those values is returned immediately, we'll still need to wait around a second. Well, because we are waiting for all of them, right? So let's, maybe to make it more visible, let's give it 5 seconds. And we are waiting approximately 5 seconds before it terminates. That looks fine. If I replace that process with just 1, well, it obviously completes immediately. But let's say there is a problem, and we have an immediate failure on the second one. So we go for throw new runtime exception. How would you expect that method to behave? Because now we have two operations. One completes immediately with an exception. Second one that completes after 5 seconds returns just the value 1. Oh, let's make it 10. Who thinks this should complete immediately and throw an exception? Please raise your hands. Okay, a couple of people. Who thinks this should just wait for all the wait anyway for all the operations to complete? Okay, fair enough. So I think you might not need that talk that much after all. So what's quite confusing in that part is that many people assume that this should just complete right away. Since I don't get any, I'm not getting any value out of that, and I know that this will never actually complete, I mean, this value is useless because I already get an exception in here. People assume that the exception should be propagated right away, but it's not the case. It turns out that CompletableFuture OLOF works in a way in which it actually waits literally for all the futures to complete, regardless of the fact if it's success or a failure. So as you can see here, we waited 10 seconds only to be presented with an exception. And that's rarely what we want. But there is a way to solve that, and let's try to do that, because it displays quite idiom that's quite often used when working with CompletableFutures. So let's say we want to fix that. So I would imagine we would just copy and paste all of that here and just try to change that method a bit. So let's call it OLOF short circuit. Perhaps we would like to make sure that all those futures, they return the same type. Perhaps let's just put a list here, would be easier. So we have a list of completable futures that we need to wait for. And instead of returning a void, it would be convenient to have a list of all the values in there. If you have a look at the original implementation, it's pretty convenient. It's pretty smart. It constructs quite a nice completion tree. So it would be nice to reuse that. The only thing we are missing is a proper processing of the return values and the short-circuiting semantics. So let's try to do that. So we can be smart and just reuse what we have out there. We go for the OLOF. And now we need, it's probably the hardest part of that implementation, which means converting a list into an array. So here's the CF2 array, new CompletableFuture, and here comes a very difficult decision. What's this right size to initialize a new array when converting a list to an array? Who thinks this should be the same size as the original collection? Please raise your hands. there are a couple of people. I hope thinks there should be 0. Okay, good to see that. So if you want to know, so this is a good example of an API that places a lot of unnecessary burden on developers. Because we know what's the right answer. The right answer is 0. And if you want to know why, there is a nice blog from Alexei Shipilev where he has like 60 pages of assembly code to explain why it's faster. But we know the right answer. And we still should have the API that shouldn't force developers to make that choice. And actually, since JDK 10, there is a new version of a toArray method where you can just provide a function, where you don't need to worry about choosing the right number. I'm on JDK 8 here temporarily, so I'll go back to the old one. By the way, the answer is that if you pre-initialize an array with the same size as the original collection, JVM will spend a lot of time initializing those empty elements, zeroing them. But they don't need to do that if you start with 0. Anyway, so here's our result with the void. And now we need to introduce short-circuiting, and we need to get rid of that void. We can introduce short-circuiting in a very easy way, because features can be completed manually, which means that we can simply iterate over all the original features and say, when that particular feature completes with an exception, just complete the original feature using that exception. Here we are introducing a gentle race, because we have a result which is supposed to be completed when all the features complete, but we introduce another part. So if there is one of those features completes with an exception, just complete the result first using that exception. By the way, this is safe. This is safe according to JMM, so don't worry about that. So once we have that in place, now the only thing left is just to convert that void into something meaningful. So the trick here is that whenever we know, at this point we know we have this void here. We know it's pointless, but if we get inside that method here, we already know that all the original features have completed, which means we can just ignore that void over here and just fall back to the original list, because we know that all the features have values inside. And if they have values inside, we can just join and obtain that value from there. Let me reformat that for you. And now, with that method, all of short circuit, if you replace that original one with it and add list integer, I need to package this into a list. Let's run it. And now there is no longer need to wait 10 seconds, but the short-circuiting is there. Plus, if we get rid of the exception, we'll get our actual values printed out. Let's not wait 10 seconds to show you that it works. Let's make it 2. And as you can see, the values are actually propagated and can be received on the other side. So this is actually quite a common issue. I've seen this in production a couple of times in more than one company. I've seen this in open source code. That's one of the issues I fixed recently. So that's a piece of code from one of the popular testing libraries. There's quite a sophisticated CompletableFuture code in here, and at the end there's just all of features. And in this part of code, you'd rather have the short-circuiting instead. So that's the spoiler. And any off. It's also pretty interesting because it also doesn't work probably the way they would expect it to work. So let's try that. So CompletableFuture, any of CF1, CF2. As you can imagine, the method looks more or less the same as the previous one, so it accepts var args of futures of any types. But this time, for some reason, it returns an object. So it accepts futures of multiple types, but already returns an object. So it's a bit better. It's pretty convenient. However, probably a bit inconsistent with the other method. Well, if you've provided futures with different types, you might need to do some instance of checks, which sucks. But at least you get a result here. But the part that people are mostly confused about is that the way it handles exceptions. So we had that result. Let's go then accept, join. Let's see what's the result. We need to end, well, so we have two futures, both returning 1 and 2 after 2 seconds. And, well, in this case it returned 1. If we keep repeating the, no, we got lucky. If we keep repeating the experiment, we'll get different values because we care only about the value that completed first. So let's replace the process with 2 to have a guarantee that this is always returned first. And that works. So let's now try to do a process something. Let's ignore that result and throw an exception. What's that? So if you are throwing exception, as you can see, we waited. So there's the first one, which we wait 2 seconds for the one. In the second one, we wait 2 seconds only to throw an exception. So as you can imagine, we have only one successful behavior, which means we got 1 out there. So what do you think should happen if the exception is the one that appears first? Many people would assume that you would wait for the first successful completion. That's also partially indicated by the fact that you have an object in here, which suggests that if there is any successful completion of all of that, you would get a value in here. However, that's not the case. So we have this process method in here. Let's make it 10 seconds again. And now we have a second future that throws an exception. And it's the exception that's propagated first. Because any of, again, doesn't differentiate between successful completion and a exceptional completion. Which means that if you hoped that you would wait for a value that completed first, successful value, well, you are wrong, because suddenly exceptions are propagated. Which is, again, I've seen this on production, I've seen bugs, and it's always a big surprise for everyone. And again, there's no easy way to solve the issue. You need to somehow deal with it yourself. It's a bit more complex than previous example, because in order to implement that, you need to start from scratch, create your own future, complete it with a success when one of the original futures is complete, and then make sure that you handle properly a case where there were no successful completions in the all original futures. But the good news is, if you need those kind of semantics, the code is very easy to look up online. But that's how we slowly move to the most interesting parts, I believe, which means CompletableFuture, threads, thread pool, execution, and what's going on underneath. So in the past, it was very straightforward, because you would have an executor service, and you needed to manually go for .submit and submit some operation in there. You would get a future. Unfortunately, due to backward compatibility guarantees, we couldn't really change it. Well, those APIs couldn't be changed. So in order to use CompletableFuture, you need to do it in a slightly different way. So let's go here. Let's go for CompletableFuture supply async. So there are static methods on the CompletableFuture class, and you create a supplier. Let's say process 42 result, and here we go. So if I go result then accept join. Let's wait a couple of seconds. Well, a bit too many, sorry. Let's make it 2. But at this point, okay. So it completed. But where did it actually run? Because if you've been paying attention, I actually forgot to do something with that executor service. It's clearly unused, right? So how come that thing executes? Where does it execute? And there are, again, a couple of options. It might just create a thread on the spot. It might create thread pool on the spot. It might have some shared thread pool to use. It might, just send it to the cloud. So there are a couple of options. And which one is that? The easiest way to check that is to just introduce a very simple check, which means in that method process over here, we'll be printing out the name of a thread that's supposed to execute it. Okay, so it turns out it gets executed on a fork-join pool, common pool worker 1. And that's a very interesting and very special thread pool. So the original classic thread pools, those are simple things. This is just a big bag of threads. In front of them there is a queue, and there are producers putting tasks into the queue and threads taking stuff out of that queue. However, the bigger the number of threads and the bigger number of producers, you end up with stuff with the thing called multi-producer, multi-consumer queue. And the more threads, the more producers, the bigger contention on that queue, which means that threads need to spend some time waiting for a task. Although despite the fact that there are tasks in the queue, threads would still need to spend considerable amount of time waiting to be able to pick it up from the queue, just because of extra contention generated by the fact that there are multiple actors putting stuff inside and trying to take it out at the same time. And at some point in time, people realized it's very inefficient. And they came up with the idea of fork-join pool, which was supposed to address one of those issues. And the design of a fork-join pool works in a slightly different way. So they figured out, instead of having all this unscalable architecture, where there's just one queue and everyone competes, tries to pull stuff out of that, let's give every thread its own queue. So in the fork-join pool, you have n threads, and each thread gets their own queue, and they are ready to just consume as it goes. When they run out of the tasks to do, they just can steal a task from someone else's queue. And it turns out to be generate way less contention than the original pool. What's more, such a design is well suited for performing CPU-intensive jobs, which means that usually in a fork-join pool you would like to have the number of threads which is correlated with the number of CPU cores. On Java it would be not number of CPU cores, but what returns that magical method called runtime, get runtime available processors, which can sometimes lie to you because, for example, your CPUs can lie, your operating system can lie to you because you might, for example, have hyperthreading. Anyway, in order to squeeze the most from fork-join pool, you'd like to have just one single instance that's shared. Because if you're doing CPU-intensive jobs, you can't go faster. You're physically bound by the number of cores you have on your system, because those are processing units that can do the actual job. So if you create multiple thread pools and start scheduling multiple CPU-intensive jobs to that, you won't get any faster. And your speed up that you gain might be slower than expected, because you need to spend time on context switching. Because same real CPU processing units, they need to do the work. But if you've over-provisioned, if you've over-scheduled, if you created way too many parallel CPU-intensive jobs, suddenly, well, it won't get any faster, because at the end of the day, it's the same cores that need to do the work. This is the reason why in JVM there is this central thread pool called common pool, which is supposed to be used for CPU-intensive jobs. However, imagine what happens if we have that foraging pool and we throw inside some blocking operations. Suddenly, those n threads that were supposed to, squeeze as much as possible from the CPU cores, they're polluted with blocking operations which just wait. And if they wait, that's not great because they could be doing CPU-intensive job instead. There are things like managed blocker and the way to circumvent the issue, but the issue still stands. So you don't want to put blocking operations in there because that's just a waste of CPU thread that could be doing CPU-intensive job at the moment. So, but what we are doing here? Look, since this is a default execution unit, I pushed process method in there, which waits 10 seconds. If I create more such methods, I can totally pollute the foraging pool with just waiting. And guess what? Parallel streams also use foraging pool as a default execution unit. So this can have a potential impact on the performance of your parallel streams. Well, you can have other foraging tasks using foraging pool. It can have an impact on that. What's more, if you've been paying attention yesterday, there were sort of discussions about Project Loom. And you probably know that Project Loom is supposed to be scheduled on the foraging pool as well. I'm not super sure how it's done in the newest implementation, but it's quite possible that if you litter the foraging pool with blocking operations, that can have an impact on the execution of virtual threads. Because at the end of the day, virtual threads need to be executed by a real thread. So as you can see, that's quite an interesting default choice to make. So if you default to that foraging pool, and let's be honest, quite often when we are using that kind of idioms, we are quite likely to run blocking operations in there. But I didn't tell you the whole truth. If we go deeper, you will see that this is where the static pool is stored. But it's not always the foraging pool. In most cases, it's foraging pool. But there is pretty much an edge case scenario where you have just a one CPU core, or by the value by available processors is 1, that it decides, okay, it doesn't make sense, let's not do foraging pool, let's do thread per task executor. And that thread per task executor is quite an interesting implementation of a thread pool. It just creates threads on the spot. And this is somehow understandable, because if you have foraging pool with one thread inside, it would be easy to totally lock everything out. So it's understandable that it's a fallback for a not a typical scenario. What's the non-typical scenario? You have a computer with just one CPU core. But if you start thinking about cloud, Kubernetes, and the world of, let's say, logical resource cap, suddenly it's not the case that suddenly you found your grandma's computer in the attic with just one CPU core and suddenly your software runs differently. But it's quite easy to end up with a problem like that, because nowadays we are dealing with one CPU more often than expected. So it's quite important to understand that this can actually influence many things. But that's not all. Here comes another interesting fact. So now we have this result over here, supply async, and let's now go for result, then apply. Well, it won't be doing anything interesting, and a few others. And those values, they return a CompletableFuture, indicating that those operation is asynchronous. Let's have a look what's actually where it's getting executed. Return I. Oh, actually, let's copy paste it a couple of times. 2 is enough. Let's join and run it. As you can imagine, that's the same thread that executed the original operation, which is, well, expected. However, let's make a small adjustment here because we don't want it to run a command. For example, we want to always provide our own executor service instance. So now we have a guarantee that it will run on the fork join on the pool of our choice. And as you can see, there's the same thread doing the work. Well, it makes sense, right? However, what if this operation completes before we even manage to register those operations? Where would that be executed? Well, we can't use the original thread because the thread can be gone a long time ago. Where does it run? Let's see. So let's remove the delay. Let's run 42. And, oh, we got really lucky. So what's happening here is that I threw this operation in here, 42. It completed immediately, and then there was no thread to execute that operation. And it turned out it did fall back to the color thread. It was the color thread that actually executed it. And look, that can be pretty dangerous because you get CompletableFuture, which indicates the operation is asynchronous. Well, you think, okay, it's asynchronous. I'll put some blocking code in here. And then guess what? It's the color thread that's executing your work anyway, the blocking operations. So you get a CompletableFuture that looks asynchronous, but it's fully blocking because, well, someone needs to run the job. This is the reason why you have all of those async methods in there. So if this is not async to you, you can make it async by adding async at the end of that operation. So now we have a guarantee that this will be asynchronous. So let's run it. Oh, wait, we are back at the common fork join pool. Because, well, that's the default. We didn't provide our own executor instance, so once again, we did fall back onto a fork join pool, which, as you can know, is a questionable choice. So finally, we add executor service in here, and we have a guarantee that now this will run fully asynchronous on a thread pool of our choice. And and unless you are doing something very trivial, let's say like I wouldn't bother if the operation was just an integer incrementation. But if you have any blocking operation, something potentially long running, that's what you always what you want to do in most cases. And now finally we have guarantees that it will all be running on the thread pool of our choice and will be fully asynchronous. And this is pretty confusing for many people. By the way, if you want to be able to run parallel streams on the thread pool of your choice, I wrote a library for that. And that's how we arrive to one final interesting part of the day, which is apply to either method and how it handles exceptions, which can be, again, pretty surprising. Let me get rid of all of that code. Let's remove even that. Let's go for CompletableFuture. Supply async, process 1, CF1, CF2. And as you can imagine, that apply to either is supposed to work. You're supposed to provide a function that's applied to either of those results. So we say it's here, and here we just go for identity function. So we go for now, then accept join. And in this case, they both complete after, we can get rid of that now. They both complete after 2 seconds, and, well, only the first one that completed gets printed out. In this case, it's 1. If we keep running, we might get lucky, we might end up with 2. If the second one is the first one to complete, we'll always get the second one first, as expected. But let's throw some exceptions into a mix. So now we have CompletableFuture 1 that completes after 2 seconds with value 1, and second that completes immediately with an exception. What would you expect to happen? Well, as you can see, the exception is the one that completed first, which means we got that value immediately right away. Although we had a perfectly healthy and perfectly fine value here waiting for us in a second. So as you can see, the same will work the other way around. So if we have this one that returns an exception immediately, and the second one that returns a value here right away, return 2. Despite the fact that we have a perfectly ready value to be processed here, we still get an exception that gets propagated right away. And that's the thing that also I ended up discovering on production and ended up being quite surprising. And this is pretty much all that I wanted to show you today. I hope you get a chance to learn something new. I still do think that the tool is really good. However, you still need to be aware about some interesting solutions that are in there. You can find me on Twitter, and I think it's time to go and check Slido. Okay, so here's the first question. Let me make it bigger. There's a question: when collecting the results, why CompletableFuture join and not get? Those are the same methods. Get and join are pretty much the same. It's just join has a bit of less bureaucracy because it doesn't force you to handle 3 or 2 types of exceptions. It's pretty much the same. But you could, all those examples would work with .get. I would be just forced to do a couple of try catches. Will CompletableFuture use virtual threads? That's a good question. I don't know about any plans about changing the default behavior. I don't think it would change because we are discussing here just the default, where by default it uses for join pool instead of something else. I don't think it can change due to backward compatibility guarantees. However, I'm not super sure if that's the part of the official contract. However, I wouldn't expect it to change. However, personally, I'm gonna rewrite my library so that it uses virtual threads once that feature is out. Given all the surprises and unintuitive API, is there any alternative to CompletableFutures? If you need the full processing power of CompletableFutures and reactive programming, you go for Project Reactor. That's pretty much the reasonable alternative. But I wouldn't probably just throw in Project Reactor to my project just to be able to circumvent some basic issues of CompletableFutures. I'd rather stick with the original one, keeping in mind the original limitations. However, Project Reactor and RxJava have much bigger power, so if you need that power, definitely go for that. How to do proper exception handling for CompletableFuture? The way the exception handling works with CompletableFuture is that whenever there is a feature somewhere in there, it gets propagated further, so it pretty much is thrown in your face when you call .join or .get. And that's pretty much where you look for exceptions, and that's all. You have some extra convenience methods that allow you to do a fallbacks or recover from exceptions, but that's pretty much it. There is nothing special, nothing fancy about that. I think we are running out of time. Okay, thank you everyone. I don't bite, so if you have questions, just grab me while I'm here. Thank you.